Thanks everybody, and thanks for having me here, and thanks for being here, especially thanks to those for whom this is not a course requirement, showing up anyway. When I advertised this talk, the tagline I used was, will audio processing be next to be steamrollered by deep learning? The answer is yes, in my humble opinion, but you might want to stick around to find out why I think that. And I also want to try to convince you that it's an interesting field of study for anybody who's interested in deep learning, machine learning. Lots of good stuff happening. I describe myself as an early abandoner of AI, as you heard in the introduction. I'm a software entrepreneur. I'm between startups right now, and in the last year or two, I've gotten kind of back to my technical roots by picking up on what's going on in the world of machine learning, AI. I used to do computer vision, satellite image stuff, that kind of thing, but took quite a break from that. But now I'm back into it, and it's really fun. I've done a certain amount of audio and video work. These are some of my products that I've done in the past, and I'm not really an expert at this stuff. I'm an outsider who's self-taught about these things, but I find that works okay if you're trying to make a product. I'm not trying to be a researcher. I'm trying to be a practitioner. So today I want to talk a little bit about what have been some of the successes of deep learning and what does that mean for audio processing. And then I want to talk about a lot of different results related specifically to audio. There's a lot of material in here, so I'm going to kind of both keep an eye on the clock and try to gauge your reaction about how much depth to go on with anything. I absolutely encourage you to interrupt me at any time with questions or comments or anything. It'll be much more interesting for everybody if we can keep it a little bit interactive. So this is just a laundry list of things that deep learning, when people talk about deep learning, these are some of the things they're thinking about where, in really just the last few years, there's been tremendous successes. The left column there is all these things to do with images, and today we're going to focus mostly on that because that's closest to what's going on in the audio world. But on the right, you see speech recognition, language, all those other things as well. I see NLP, or I say NLP, sort of natural language processing, because there's also a question hanging over that. Is deep learning going to steamroller over everything that's going on in NLP? And the jury's still out on that. But I want to look at all this from the perspective of what can we learn from all this for audio. And what do I mean by audio processing? There's lots of different applications where the things I'm talking about today could play a role. The one I'm particularly interested in is hearing aids, trying to make a better hearing aid using these technologies. And I could talk for an hour about all the problems with hearing aids and what needs to be done, but I'll mostly stick to the technology here. The list of things on the right-hand side, the tasks, they're useful for almost all these different applications. And one of the things I think that makes audio applications a little bit challenging is that you have to make progress on that whole long list of things, basically, before you've got an end-to-end system that's really going to work. So let's start with image classification and ImageNet, which I'm sure everyone here is familiar with. But this is the thing that really kicked off this current wave of new results in deep learning. And I want to focus on ImageNet just for a second, just because it's very relevant to the world of audio and makes an interesting contrast to what's happening there. So ImageNet is both a collection of data, a whole bunch of images with labels on them in 1,000 different classes, but it's also a competition with very clear criteria for what it takes to win the competition. And that's held every year. Each year, somebody wins, and the errors have been going down dramatically, sometime around 2015. The computer's ability to classify these images actually outstripped human beings' capabilities in terms of accuracy. It was around 2012 where those bars changed color when deep learning techniques took over from standard computer vision techniques, or I'll call them traditional computer vision techniques. So if I use the words traditional here, I just mean stuff before deep learning. Nobody should take offense by that. And basically, yeah, around 2012, deep learning won ImageNet and never looked back, and the results continue to get better and better. So what does this mean for audio? Well, the specific techniques of classifying images might have a role to play for audio. There are cases where we want to identify what was that sound that we just heard. If you're in a car, you want to know, was that sound, was it a siren, or was it somebody honking at you, or was it just like traffic noise, for example. But I think the real lesson from ImageNet is that if you take the right problem and you make the right data available for it, it can propel the whole field forward. And I don't want to overstate it, but I think ImageNet was really instrumental in kicking off all these results that we've seen being so dramatically good in the world of image analysis and using deep learning. Now, there are audio competitions out there. Chime, Reverb, there's a few other things. I'm guessing you've all heard of ImageNet, but you haven't heard of any of these other competitions. So the audio community has a little bit of a marketing challenge there. None of those has quite caught on the way that ImageNet has. In terms of the data side of things, though, there is some good news on the audio side. There are many, many data sets, and people have been working on audio problems and speech processing problems for decades, and over that time, they've accumulated lots and lots of good data. Unfortunately, some of that data is a little hard to get, particularly like for an independent researcher like myself who's not associated with an academic institution or otherwise sort of connected in. It's a little bit behind a paywall that's hard to get through. But there's... what's that? Yeah, it won't get you past the paywalls for the data, though. It'll get you past paywalls for other things. Not that I would ever use such websites. But the good news is there are open source sources of audio which are kind of spectacularly good for the type of applications that I'm going to talk about today. There's a website out there called LibriVox. You may or may not have heard of that, but it's people who just volunteer to make public domain recordings of public domain books. There's like 10,000 books that people have recorded on there, and these are like full-length novels, lots of them, so they can be 5-10 hours long, maybe longer. And they explicitly say this is all public domain, do whatever you want with it. So many, many hundreds of thousands of hours of recordings there. Somebody had the bright idea that this could be a good data set for doing research, particularly with respect to speech recognition, that kind of thing. And so they went through and they got 1,000 hours of this speech, all in English. There are other languages there, but they just stuck to English for this. 16 kilohertz, that's actually pretty good quality. But the real effort that they put into it, and the important thing they did, was to take the text of that and carefully align it with all that audio. And that was a kind of a tour de force, but very important. What's great about the LibriVox is because they're reading from known books that are readily available, we've got the ground truth words that go with the audio. So that's cool. Anyway, LibriSpeech is out there. It's a big data set. It's very high quality. It's licensed in a very friendly way. And as we'll talk about in a minute, if we want to take, it's nice clean speech in LibriSpeech because it's all closely recorded with people mics close to their mouths. If we want to add noise to that, background noise, simulate what it's like to be in a coffee shop and what you might hear, that kind of thing. There's lots of sources of that kind of noise. For reasons I don't fully understand, people will set up a microphone on the street or in a coffee shop or somewhere else, just let it record for like a couple of hours and then upload this to YouTube. I guess some people like to work with coffee shop sounds or something, so they put that on as background. So the good news is, again, audio, there's lots of data available to us. Okay, back to images and image classification. This is a great example, and one of the few that we have, of transfer learning. These networks that win the ImageNet competitions are generally made available for people to access, but not just the code for the network, but the actual trained network. So all the weights that have been learned are there. And there's many, many applications where people will take a pre-trained network and they'll grab results from somewhere in the middle of the network and do something with that, as opposed to just, and they'll replace the back end. So the end result they want is not necessarily a classification of the image. Instead, they want to have this representation of what's in the image as learned by the network. And so I make the statement here that we've learned a lot about the structure of natural images from this. What do I mean that we know something? I mean in the sense that we have this reusable representation of images, which is pretty abstract. We don't really know what's going on inside the network, and there's lots of things that people do to try to understand that better. But it works, and there's these intermediate representations that prove useful in other domains. So apparently we're learning something that's real about these images, and the applications generalized images that the network has never seen before. So there's just something about natural images that we know. That's not really the case for audio. We're not at that stage yet. And I often get the question when people find out I'm working on audio, oh, what's the equivalent of ImageNet for audio? And there isn't. And what's the equivalent of pre-trained network for audio? And I'm not really aware. In specific circumstances, sure, there's some reuse. There's some speech recognition models that you can sort of get off the shelf. But so in the sense that we have learned a lot about natural images, it would be great if we could also have a model of clean speech, and in some sense, to use. We'll see some of the work we'll talk about today is headed in that direction. It's worth reminding ourselves why it is that deep learning is having such an impact these days, and then ask the question, what does that mean for audio? First thing is, there's lots of data. We're in the world of big data now, and that is an important angle here. It's also a good fit for these neural networks because they're very high capacity models. They're the way that we can take in tons and tons of data and get better and better. More traditional techniques where we're doing physical modeling or other kinds of sort of handcrafted features, it's hard to just take in a whole bunch of data and do anything with that. Instead, we rely on our ability to do the modeling well. So lots of data. The hardware's gotten better. The rise of GPUs for this is well known and plays a huge role in it. And anybody can now have this very powerful GPU in their home for $1,000. The net of that is that it's made experimentation much more feasible in the world of deep learning. The dirty little secret about deep learning, which is not a secret at all, which is that there's not a great theoretical foundation for almost everything. It just works way better in practice than in theory. And the way we get better at it has a lot to do with doing a lot of experiments and just getting empirical results and making choices because this thing works better than this, as opposed to having a good understanding. Everybody who does deep learning would love to have that understanding, and lots of people are chipping away at that. But the reality is it's an experimental science right now. So what does all mean for audio? Is it ripe for deep learning? Well, yes, deep learning has shown that it's generally good for signal processing problems, and that's what audio is. I'm calling images signal processing. Yep, go ahead. So the question is what we've seen with deep learning is that it learned the features, the networks learn features that previously had to be handcrafted, and are we seeing the same thing for audio? Not yet. I mean, a little bit, and we'll see some of the successes in audio deep learning, and there are some, for sure. It's that same observation applies. People are not handcrafting the features that are being used. Instead, the network is learning them. Okay, so deep learning is generally good for this type of problem, so we should expect good things. We have lots of labeled data. There's an asterisk on that. The asterisk is we have lots of data if we're allowed to synthesize the data, by which I mean, say the problem we want to do is to take a noisy recording of speech and clean it up so we just have clean speech. Well, the ground truth for that would be a clean speech recording. And we have lots and lots of clean speech recordings. I just mentioned LibreSpeech. There's many others. But it's also easy to add noise to that in a pretty convincing way. Physics is on our side here. If you have a couple of noise sources combining together, they just add up. It's just a linear superposition of those signals. So if we want to have a couple of people talking with some background noise, we can take those separate sources and just mix them together. And that's not a bad proxy for just recording out in the real world. It's not exactly the same, and it's not guaranteed that by learning on the synthesized data that it will generalize to real recordings. There's many different kinds of noise, sure, yes. But most of the ones that you care about, there's some semblance of there's some recording that's probably a good proxy for that. So we can add noise that way. I mentioned reverb here, just room echo. There's lots of models of rooms, and people can pretty convincingly synthesize the effect of reverb. If you go into any standard audio editor, you'll have a choice of 20 different rooms. Do you want to record something that's very flat and clean, but make it sound like it was recorded in a cathedral? Yeah, you can just flip a button and it runs a filter over it and it does that. So the forward problem of starting with clean speech and making degraded and speech with artifacts, that's pretty well known how to do that well. What deep learning wants to do is to do the reverse, but it means we've got lots of ground truth to work with. And the other thing that's going in favor of audio is that we have all these image techniques that may or may not apply to audio. We've got lots of people working on image stuff. Maybe we can just steal all that stuff. Oh, I'll mention this business of synthesizing data for audio. That's an advantage of audio over images. We don't have a great way to synthesize images in any way that's very convincing about what's out there in the real world. You can fuzz them up and stuff, and you can apply, I suppose, lens filter type things, but not nearly as much. And people don't do it as much as they do in the audio world. Okay, so yes, yes.
So audio work is lots of different applications like speech process, recognition, synthesis. Are you talking about the general statement that applies to all, or are you focusing on any particular application?
Well, I'm thinking about a few different applications. I'm not talking much about speech recognition today. That's a different area, and it's one where there's actually been deep learning has helped a lot. But I'm thinking more of, again, if we think of the hearing aid type of ultimate application, that's one where you need to solve problems of reducing noise and separating sources from complex mixtures, and generally enhancing speech. Those are the kind of applications I have in mind. All right, so how is audio like images, and how is it not like images? When we work with audio, we work with it in one of two possible ways. We have the time domain recording. This is the thing that is recorded on, when you go to Spotify and listen to something, it's sending a time domain signal down to your earbuds. It's just sampling the amplitude of the signal at regular time steps. Then there's the spectrogram shown on the right there. This is where over little time windows you calculate the frequencies and the magnitude or amplitude, amount of energy at each frequency bin at that time, and see how that evolves over time. So the x-axis is time, the y-axis is frequency, and the colors are the magnitude of the energy that's at that frequency at that time. There's not like debate exactly within the community about these, but people will use one or the other approach. Certainly, approaches based on spectrograms and traditional processing have been very popular, and there's a ton of work that's done that way. The time domain has generally not been thought of as a good place to do processing, and that frequencies are more, closer to what's interesting about sound and where you need to be manipulating things. So, lots of that. The reference at the bottom there, comparing time and frequency domain for audio event recognition using deep learning. They looked at a specific task. They concluded that, in fact, the frequency domain was better in their particular case, and that's the one you should focus on. And there's lots of studies that way. But there's things that go either way, and we'll see some interesting results in the time domain pretty soon as well. So one of the challenges with using spectrograms is that you end up sort of throwing out half your data. And this is the challenge of phase. So audio has both amplitude and phase. And a spectrogram, I mean, the good news about it is this time domain and the spectrogram, they're equivalent in the sense that you can go from one to the other and back again perfectly. But you can do that perfectly only if you keep the complex values of the spectrogram. So you apply a Fourier transform, you're going to get complex values out of that. That's fine. You keep all that, then you can do the inverse Fourier transform, and you'll get back to where you started. That's great. However, the typical processing scenario has been for a long time is you start in the time domain, you make your spectrogram, but then you split your spectrogram into the amplitude spectrogram and the phase spectrogram. You don't do anything with the phase because it's too hard to work with. You do some modification of the amplitude spectrogram, maybe find some noise, get rid of it there. Then when you want to get back to create your output signal, you take the original phase, combine it with your modified amplitude spectrogram, and then invert that to get your signal. Now that sounds like kind of a bad idea because we're taking like bad phase information and reusing it. Yeah, everyone kind of knows it's a bad idea. So but you know, you kind of get used to it in a way, just for practical reasons. What can you do about that? Well, you could modify this phase spectrogram, but it's too hard. There's just not a lot of structure there. We don't have a good way to deal with that. Very noisy. You could, in fact, work with a complex spectrogram end to end. And I haven't seen a lot of that being done in traditional processing techniques, but in some of the deep learning approaches, they do that. Instead of taking real values into the network and doing something, they'll take complex values and trace that all the way through. I've just given some links here. I won't go into a lot of detail about that. But they're getting some, you know, okay results. It's early days for that. It's not as simple as you might think. Like it sounds like, well, it's just complex numbers and there's just twice as many of them. How hard can it be? But all the things that you use in deep networks in terms of loss functions and activations and so on, all of a sudden takes on a slightly different flavor when things are complex. Mostly because real numbers are ordered and complex numbers are not ordered. However, they figure it out. The third thing that you can do is to work in the time domain. Just work with that time domain signal. Forget about going to the spectrogram at all. This has its own challenges because there's like tons of data there. A high quality recording is being recorded at 44.1 kilohertz. So you're going to get thousands of samples every second, or even over the small fraction of a second you might be doing analysis on. You're still getting with thousands of samples. And the interesting stuff happens over many different time scales. If you've got high frequency things going on, that's fine. They will occur over a relatively small number of samples, and you can detect that. If it's low frequency, that's spread way out. And you know, how do you deal with that? Okay, well let me leave that thought for a minute. And as you'll see, I have to kind of skip around topics a little bit. It would prove impossible to do a sort of a linear pass through all these topics. But we'll come back to some of those thoughts in a minute. Okay, convolutional neural networks. Again, I'm sure everyone in this room is very familiar with these, but it's worth thinking about them from the perspective of audio processing. So CNNs have been just spectacularly successful for images. And why is that? Well, the weights are sparse. In a CNN, there's a translation invariant, like the feature that might be interesting. It could occur anywhere in the image, and fine, CNNs are capable of handling that. And it makes an economical use of weights. There's a lot of weight sharing. So it means you can have a relatively small number of parameters, still in the millions probably, but not billions or trillions that you might have to if you had you know, fully filled in non-sparse kernels that you were dealing with. But why does that work for images? Why is it so successful? Well, the reason is that images have local coherency. The value of a pixel at this point has a lot to do with the pixels that are right around it, and you know, less to do with things that are farther away from it. There's a certain symmetry in the x and y directions. Images, if you take one and rotate it by 90 degrees, it still looks like an image. It may look, the horizon's now looking funny, but it still looks like a natural image. And as far as the computer's concerned, it's still good. So there's that symmetry. The image semantics, like what is it that we're looking at in this image, seems to be kind of hierarchical, and we'll see that here. So as we go deeper into a CNN network, convolutional network, where each layer of that network is looking at more of the input pixels, ultimately, because it's sort of aggregating these things as we go through the network, and it's learning higher level features as it goes. So at the lowest level, at the first layer of the network, you're seeing edges, and then you're seeing maybe textures, patterns, and you get higher level things. You compose those together at the end, and that's what lets you identify what's going on there. And as we talked about earlier, the CNNs, they learn the features themselves. That's very nice. So what does all this mean for audio? Well, if you're in the time domain, a convolution makes sense. It'll be a one-dimensional convolution, but it still makes a reasonable amount of sense there. You've got local coherency. The features that you might be interested in could occur anywhere in the time stream, so you want that kind of convolution effect to happen there. So that's all good. What about the spectrogram? It looks like an image, right? Why can't we just take all these image results and just use it on the spectrogram? Well, some people do with, some success, but it's probably not going to be the very best way to do it, because the x and y axes here are not symmetrical. They don't have the same kind of information behavior. You've got time running this way, and it could be as long as you want. In the frequency dimension, you've got actually pretty low resolution there, typically 129 frequencies or something like that. Plus, the coherence in the y direction between frequencies is not the same as it is through time or in an image xy. Because you have harmonics. You've got your base frequency, and then you've got harmonics at multiples of that. So there's some long-term relationship, or across long-distance relationships that are important for understanding the structure of that sound, if you're trying to think of it that way. So that makes it all sound like I'm leaning toward doing time domain processing. You're right. This paper that came out last year, WaveNet, really caught a lot of attention, has been extremely influential in a lot of audio processing that's happened since then. And you'll notice the time frame I'm talking about for a lot of these audio results is quite recent, within the last year or so. There are things in this presentation today that just came out a few days ago. And there's things where I said, gee, how come nobody's done this? And then the next day it shows up on arXiv that somebody's tried it. Okay, so WaveNet. WaveNet is, I think, a little bit unusual in where it came from, because the authors were first interested in coming up with a model for natural images. That's had much less impact than when they took that approach and applied it to audio. And their best results have been for text-to-speech, for synthesizing audio. So they're very interested in generating audio that sounds realistic. Everything's done in the time domain. And the general idea is they have a probabilistic model for speech. So X here is that's our a signal of natural speech. They're saying, okay, we want to learn the probability density of X based on, at a particular time t, based on everything that's happened before that. That's the structure of the probability that they want to learn and discover. They did a couple of very innovative things along the way. Dilated convolution, which we'll talk about in a second. They didn't invent that, but they certainly, I think, popularized it for many. We'll see about that. They also treated the audio sample values as discrete values as opposed to continuous. Almost all work up to this point, whether it's probabilistic or otherwise, would say, okay, the amplitude that we're seeing, it could be any floating point number where we're sampling from a continuous signal. They're saying, in reality, you quantize when you do that sampling, and it works out better to actually think of these as quantized samples with discrete values, not continuous. So dilated convolutions, so I'm assuming everyone knows what regular convolutions are like. Dilated convolutions are those where, as you go up the layers, and this is like a sort of a, think of this as a single convolution operation, even though you're seeing multiple layers. So you might look at from the input layer, you'll look at a couple of pixels perhaps. The kernels are typically 2 in size. So you're looking at a couple of, or samples, not pixels, but a couple of samples side by side all the way along. The next layer, again, you're looking at 2 samples, but now they're spaced apart by 2, and then by 4, and then by 8. So you have this exponential sparsity that you introduce, and it means that within a relatively few layers, you're now looking at a whole bunch of the input. Versus if you stack up normal convolution layers, you're getting kind of a linear increase in what your receptive field is and how much of the input is influencing your results. With these dilated convolutions, now you're seeing much more. So that's good news. Remember, we're in the time domain here with WaveNet, and I was saying before about the time domain that you want to, you have to take care of the fact that interesting things happen potentially across very long time scales, and this is a way to get at that. So the architecture here, I won't go into great detail on this, but there's, so you get these convolutions down here. You stack them up. You put in a residual blocks. This is like recurrent neural networks type of a style. So that is going to capture some of what's going on as this signal evolves through time. And you feed all this finally into a softmax, and that's where you make your prediction as to what the next sample value would be based on what you've seen before. Okay, so they do a bunch of things with that. Let me play you some examples. Finally, you'll get to hear some audio. And these examples came out with their paper last year, and they're comparing here with a couple of standard ways that people have used to generate speech before. And today on your phone, probably this middle and concatenative is what you could do.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
It's not terrible, but it's kind of computer-ish.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
And here's WaveNet.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
In this room, the differences are a little bit subtle, but believe me, if you're listening with headphones or closely, it's quite dramatically better. No, these are synthesizing speech from text, and so it's a generative model of speech. So it's text to speech, and the thing you're trying to do is to do that in a way that sounds like a human rather than like a computer. There isn't an objective measure of that. That's a great question. We'll come back to lots of performance measures. It's just, right now, it's just subjective listening is how we decide that it's good. Sure. Well, no, not, excuse me, not so much. But we'll can I come back to that? Because it's actually a difficult question as to what is the objective measure for quality speech. I'll give you another example here, and then we'll move on to other things. Okay, parametrics is a couple of years ago.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
A little more recent.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
And then WaveNet.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
So again, in this room, these previous techniques were not terrible. If we went back 10 years, yeah, you'd really notice. But WaveNet does sound significantly better, for sure. So that was a year ago. The problem was to generate those sound samples took an enormous amount of time and computing power. it was many, I don't know, I think minutes per second of output audio that it would take. I won't play all of these, but recently they published more, and now they're at 20 times real time in terms of the generation capability, so it's very fast. And
A single wavenet can capture the characteristics of many different speakers with equal fidelity. A single wavenet can capture the characteristics of many different speakers with equal fidelity. Now, it's fast.
now it's very fast. I'll do one more, just I think this is a different type of voice. Well, actually I'll do the Japanese voice, just to indicate that it can do many different types of voices.
一つのウェーブネットのみで多数の異なる話者の音声波形を極めて正確にモデル化できます。一つのウェーブネットのみで多数の異なる話者の音声波形を極めて正確にモデル化できます。今回、ウェーブネットによる音声波形生成を劇的に高速化しました。
I don't know Japanese, but I think the last part was now it's fast. Again, to really appreciate this, you'd have to sort of go online and listen to it. But this will be, the new WaveNet will be in your Android phone soon, and you'll probably notice a significant improvement in that context. All right. Back to images. What are some of the other things we do with images? Well, we started out by classifying things, and that evolved into detecting objects within images. Images are not just one thing. They're collections of things typically, so that's good. And that evolved into very fast techniques for classifying things within a video. This is the sort of thing you might want to be important for like a self-driving car, to be able to recognize pedestrians versus bicycles versus storefronts and that kind of thing. The main point to bring this up is there a relevance to audio here? Maybe a little bit. Speaker diarization is what you do if you have a recording of a few people and you want to track one speaker and keep track of what that person is doing and separate that out from what the other person is saying, that sort of thing. So those sort of tracking techniques might be valuable there. But the bigger picture is that we started with ImageNet. We're classifying these images. Let's face it, that's a little bit of a toy problem. If that's all we could do, it doesn't really solve any real-world problem. But having worked on those problems, now all of a sudden we're helping our cars drive themselves. So super important. Some of the things I'll talk about for audio, you'll kind of wonder, well, it seems like that's not very important if we could do that. These things do lead to much more interesting results. Image segmentation takes this even a step farther now, the idea of object detection. This is now getting closer to things we actually want to do for audio. So in the case of image segmentation, what we want to do is to not just identify object in the image, but label every pixel in the image as to what class it's in. So on the left-hand side, we're seeing, again, something that might apply to a self-driving car situation. The different colors represent different categories of things in that scene. Roads, trees, cars, lights. I don't actually see any people there. Oh, there's some people. Yep, people. This also has applications in medical imaging. You want to distinguish what are the boundaries of cells and distinguish different types of cells from one another. So there's a technique that has become very popular just in the last couple of years for doing that kind of image segmentation, and we're going to see it showing up in audio a lot, so I'm going to take a second to talk about it. It goes by a couple of names. They're related. Fully convolutional network, FCN, or UNet. UNet seems to be the name that's sort of winning because it's shorter and it's got a pretty picture that goes along with it. So what's going on here is that we have convolutional networks. We take our input image. It goes into a few layers of a convolutional network. But then we make it smaller, typically through max pooling. We'll lose some spatial dimension. But at the same time, we're increasing the frequency dimension here. So whereas we said this is like for just a grayscale image, so we've only got one feature layer, like the gray level values here, one dimension there. But in our convolutional layer, we do 64 filters, 64 features, and continuous 64. At the same time, we reduce the spatial dimension. We increase by a factor of 2 each way. We increase the feature dimension by a factor of 2. So we're actually doing dimensionality reduction, because it's 2 squared versus 2. We're losing spatial information, but we're gaining information about features. So you repeat, repeat, repeat. You go through this bottleneck down here. But then you go back up the other side, and you basically do reverse kind of operations all the way through. So you're, on the one hand, decreasing the number of features, 512 here down to 256, and at the same time, you're increasing the spatial resolution. There's a number of different ways that you can upsample the resolution to the next size. And typically those ways are learned as part of the network. It learns how to do the upsampling as part of all this. The net result of all this is that you had an image of a certain size going in. You get another image of a different size coming out. The image coming out is the one where all the pixels are just a few colors representing the classes, but it's the same size. So very different from the classification problem where you have an image in and then just a label coming out. This is image in, image out. So that's very relevant to audio because we're typically wanting to clean up some audio, and the output we want is audio. We don't want a label on it. So these kind of transformation problems, the image-to-image transformations, have a direct bearing on sort of audio-to-audio transformations, and we'll see they get used a lot. Things like denoising, source separation, those kind of problems in audio are essentially segmentation problems. If you've got two people talking, you want to segment, you sort of want to label everything as, is it person A or person B that's talking now? And I mentioned a couple things there, but we'll see more there. So okay, we're going to park that thought. We're going to talk about noise reduction, and we'll come back to what UNets have to do with that. So noise reduction is a very classic thing to want to do with audio signals. The traditional way to do it is you open up your favorite audio editor, and you open up the file. The stuff that's here at the left is an example of the noise. This is actually a person talking, and we'll hear this a little later, but a person talking with some coffee shop kind of background noise that you want to get rid of. At the beginning, the person isn't talking, so we've got a nice little segment here where it's just coffee shop noise. So you select that segment, and you say, okay, you probably can't see this. This says capture noise print. So you tell the application, this is the noise. Then it says, okay, here's what I learned about that noise. And you have all these knobs and dials that you can turn to adjust how it's going to apply a correction based on that noise. That graph of the little dots that you can probably barely see in the middle, yeah, not at all. Anyways, the frequency response of the noise. And it looks kind of flat because the noise is pretty nondescript. And in fact, if you then say, okay, go ahead, it makes almost no difference. So the kind of noise reduction that works with traditional techniques is not the kind of noise reduction where you get rid of coffee shop sounds. It's more, if we look at the spectrogram of that same image, one of the things you might be able to see is like across the middle here, we have this pretty bright line. That means that at that frequency, there's this kind of steady pitch, hum, squeal, something like that. This technique would be good for getting rid of stuff like that. But if you look at the beginning of the file, there's this basically nondescript mush of different frequencies and things, and it can't really do much with that to help you out. So this is the technique that gets used in your typical audio editor is a spectral subtraction or some variation on that. That's evolved over the years. It can do a great job in very specific kinds of noise, but it can't solve the problem that we want to solve, which is to get rid of ambient confusing sounds. So back to WaveNet now for a second here. What can we use WaveNet to help us denoise speech? So these folks took some of the WaveNet concepts. This doesn't look very much like WaveNet anymore, but bear with me for a second here. So on the left, we have a noisy speech fragment that feeds into this pyramid. This is the dilated convolution cell that's happening there. They've got skip connections, blah, blah, blah. It goes over here. Denoise samples come out the end. So they're using, the main thing they've taken from WaveNet is this dilated convolution idea. the L1, the loss on the samples, and this is a little bit to the question that you asked earlier. In this case, it's just an L1 loss. They're just looking at the absolute difference between their clean speech and their reconstructed speech. They're actually using non-causal convolutions. So when I showed you the WaveNet thing, it was always looking backwards to do those convolutions. This looks forwards and backwards. That helps. They do several at once. It doesn't really matter. I say it's mostly not like WaveNet because really they kept changing things from WaveNet, and by the time you get to the end, you've got dilated convolutions, and that's about it. There's a fully convolutional architecture, though. They don't do any pre-processing, and it's end-to-end in the sense that you've got audio in, audio out. Everything in between is what you're training and what it's going to do. So there's some sort of objective measures. MOS is actually human beings listening to it and rating it as to how well they like it, and then these numbers mean that they like the WaveNet version better. I'll play it for you in a second, but let's go back to this sample. Just look at it in the time domain, and what we're getting out of this is that that's the noise. Now, if we apply their way of doing the noise reduction, all that stuff, like in particular over here at the beginning, like it just gets clamped down to almost nothing. And the stuff in between where there was the background noise showing, I'll sort of flip back and forth a little bit here, you can see it's done something pretty dramatic to that sound. Okay, dramatic is not always good. Let's see, and again, I think these things are going to be a little bit subtle. So I'll play the noisy first. Wiener refers to a Wiener filter, a traditional kind of approach to doing noise reduction, and then we'll see what their WaveNet version did.
Some have accepted it as a miracle without physical explanation.
So a little hard to hear maybe, but he's talking over some background noise of, I think there was some music in a coffee shop, something like that. Okay, here's a traditional Wiener filter.
Some have accepted it as a miracle without physical explanation.
You can still hear a lot of that background stuff going on there, even in this room.
Some have accepted it as a miracle without physical explanation.
You hear a touch of the background, but much suppressed. What you probably can't hear in this room, if you're listening more closely, is that the voice definitely has artifacts on it, though, of an odd type that you probably haven't heard before. Let's one more example, then we'll move on.
It may well have been.
Maybe not that one.
However, at the intensive care unit at the Southern General Hospital was full. I was furious. I was furious.
Yeah, all right, I'm going to go to this one.
It may well have been.
Some playground noise in the background there.
It may well have been.
The thing you can't hear in the Wiener thing is you get this sort of garbly musical type of distortion that happens as well. Sounds like the person's talking underwater. That is gone with the wavelet.
It may well have been.
Again, a little hard to hear in these circumstances, but WaveNet is definitely doing better at noise suppression, but it's adding its own kind of artifacts to it. Still a very, very interesting approach. This next paper is one that I really wanted to love, and I'm still trying to love it. I like the approach that they're doing. I'm not completely convinced by what they've done, but let's talk about it for a second here. So they want to use WaveNet, and they want to take this Bayesian approach to doing noise reduction. Their philosophy, I think, is pretty great. The old way of doing noise reduction, which we saw when I was in the audio editor, is you want to model the noise, find that noise within your signal, and then suppress it. And they're saying, no, let's turn that around. Let's model what clean speech sounds like, or is, and anything that's not speech, we'll call it noise, and we're going to enhance the speech rather than suppressing the noise. So they have a probabilistic speech model building on the one that WaveNet has. And they're eventually going to learn the prior model and the likelihood model from the data. So their probabilistic model here is they want to come up with a probability distribution for clean speech, that's X, conditioned on the previous predictions of the clean speech. So it's, again, this incremental thing that they'll do. And Y, which is the observations of the noisy speech. So through the magic of Bayes, they can split that up into these two models, the prior model and likelihood model. And they train those independently and then combine them together after that. So This is, believe it or not, looks like WaveNet. Now let's listen to the examples, and these are going to sound a bit strange. So first of all, the noisy example, and then we'll hear their cleaned up version.
She then spoke of the letter repeating the whole of its contents as far as they concerned George.
That's very annoying. It's also not the type of noise you typically want to get rid of, but it's also the type of noise that would be super hard to get rid of through many other techniques. So what does it sound like after they clean it up?
She then spoke of the letter repeating the whole of its contents as far as they concerned.
So I think in this case, you could hear that the clean speech is still, it's pretty scratchy and not spectacular from a quality perspective. It is much more intelligible, though, without that interfering sound. And we'll hear that in a couple of these other ones, too.
No more have I, said Mr. Bennett, and I am glad to find that you do not depend.
Even with headphones on, it's really hard to hear what that person is saying because somebody's opening scissors next to the microphone, or I don't know what that noise is. So let's try this here.
No more have I, said Mr. Bennett, and I am glad to find that you do not depend.
So, very scratchy sound, not high quality speech, but very much more intelligible. One more example and we'll move on.
Whether Mrs. Collins has yet expressed her sense of your kindness in coming to us. Whether Mrs. Collins has yet expressed her sense of your kindness in coming to us.
So one person I played this for, they said, well, that sounds pretty terrible. What a waste of time that was. I said, no, you're wrong. Those type of noise is super hard to clean up in any way. And the fact you get something that's kind of intelligible out of that, this is a good first step. I say I want to love this paper. I'd love to hear it applied to more realistic kinds of noises, for example. And but this notion that you can separate out the training model where you train first on clean speech, which is this prior, versus the noise, which is specific to the example you want to clean up, that holds out a lot of promise for transfer learning. So somebody, Google, who's got lots of resources, could give the world a model of clean speech, and then we could use that farther. Yes? You mean you could obscure what you're saying through all that noise?
I'm saying that if I'm a spy and I've got this technology.
Probably. There's bad uses for all of these things. But the other thing I would think of, again, in the hearing aid context is, you really want to enhance the speech in the presence of all kinds of interfering sounds. And the notion that, philosophically why I love it is the notion that speech is this fairly structured kind of sound that we have a chance of modeling well, and everything else will suppress. If that program can be made to work, that would be really powerful. Yeah? As far as I know, no. Now, they did their training on a very limited training set. In fact, they just trained with one person. And then the test was on the same person, which is also a reason I'm waiting to see better results. But it's likely, but unproven, that you could generalize from one language to another, that speech is probably reasonably similar from language to language. But to best results, I'm sure you'd want to train on several languages. Yeah. Yeah, if it did a perfect job, yeah, it would suppress the horn. Yeah. So you don't always want to suppress those interfering sounds. Sometimes they're important, for sure. Generative adversarial networks is something where you get kind of spectacular results in the image world. All these pictures are not real people. These are pictures that were hallucinated by a neural network. And they're pretty good. They started with a celebrity database, and they just invented a whole bunch of new pictures of people that look like celebrities. And they do, right? I would say we have passed through the shadow of the valley of uncanniness and come up the other side. Although if you look at them long enough, it starts looking a little odd here and there. But that's pretty amazing. What's that got to do with audio? Well, lots of things. We want our audio to sound better. We want it to sound more realistic. Just like we wanted those pictures to look realistic, we want our audio to sound realistic. So this paper takes this idea and does speech enhancement using a generative adversarial network. So if you don't know how these GANs work, basically there's two networks. There's a piece of it that generates, in this case, generates audio. And then you have a discriminator network, which you train to learn what is fake audio from what is real audio. And it's called adversarial because these two things kind of work against each other, and you train them back and forth. So the generator is trying to fool the discriminator. The discriminator is trying to properly detect what the generator has given it. This is all done in the time domain. Again, so again, that's pretty interesting. It models it end-to-end, audio in, audio out. And this gets right back to the question of what is the right loss function to use for audio? What's our measure of whether it's good audio or not? It's hard to come up with something just sitting down and trying to think of it. So instead, we let this GAN effectively define the loss function for us. That's what it's doing. It's learning the loss function for us. So they trained this up on a whole bunch of things. The generation network here basically is a UNet kind of thing. Let's see what we've got here as results of this. Again, don't get your hopes up too high, but it's something. So noisy speech.
We were surprised to see the photograph.
That's pretty noisy. Traditional noise reduction. Whoop. That didn't work. Hang on. Right, so let's do the noisy speech again.
We were surprised to see the photograph.
Traditional.
We were surprised to see the photograph.
So still lots of noise and lots of garbling.
We were surprised to see the photograph.
A little bit of garbling, a little bit of leftover noise, but much, much less. Let's do another one.
It's too early to say whether a public inquiry would be appropriate.
That one's not very noisy. Let me try this one.
He says that he is no different from any other man. He says that he is no different from any other man. He says that he is no different from any other man.
The result's not dramatic there. Yeah, should have thought that in a room like this it's going to be harder to hear. But again, if you go to their website where they have all these examples, the noise is pretty convincing noise. It's realistic, and the Wiener filtering does not do a great job of it, and it adds a lot of its own artifacts. The Sagan results, definitely much less noise and pretty interesting results there. But early days, lots more work to do. Another thing, and I'll mention this fairly briefly, where deep learning is having great success with images is in painting or filling in gaps, essentially. So you can see that they've just masked out portions of these images and then filled them back in. And if you've ever used Photoshop and its content-aware fill, you'll sort of have an idea of what this is trying to do. But if you try to use content-aware fill in some of those extreme cases, it won't work very well at all. The technique here, again, you'll see this sort of the completion network, they call it. Again, it's sort of this UNet type of structure. They do something locally, they do something globally, and it really works well. This is a paper that just came out. What's this got to do with audio? There's a very common source of noise for audio, which is that the person recording the audio, probably me today on this thing, some of it will be too loud, and it just like the A to D converters can't handle it. They just clamp it at some maximum value. So the extent the waveform was above that value, you've lost that information. So effectively, this is just gaps in your data. They happen at irregular intervals, and there's no good model of how to fill those in. You can definitely go to your good audio editors and apply declipping filters. They don't work very well. They really don't work very well. It seems like this would be a natural for deep learning to be applied here. But as far as I can tell, nobody's working on it. So there's a problem for you. If you can solve this, you'll have a good product that people will buy from you. Mm. Right. Yeah, that would be an interesting application. So you're saying video and even just images. You can blow out your whites at the high end, or you can crush all the blacks at the low end. Yeah, if you want to add some more dynamic range, maybe there's an HDR type of application for something like this. But I don't care about that. I care about audio. I want you to fix my clipping distortion, please. Like how many samples in a row are clipped, you mean? Or you would lose, I mean, obviously there's degrees of severity, but typically 100, 50, 100, couple hundred samples in a row. Yeah. Oh, I mean, say you're recording at 44 or 48 kilohertz, you might lose a few hundred samples in a row due to clipping. Yeah, it's oversampled. Well, it depends how high the frequency is you want to capture. But I mean, if you're trying to capture good quality sound, voice or music, sure, you might want everything up to 20 kilohertz. So you need that. But clipping distortion is you really notice it. It's a very harsh sound, very unpleasant to listen to, and it can really ruin a recording. So anything that could clean that up effectively would be good. And I've certainly been guilty of recording stuff with clipping in it, and I tried all the tools out there, and it couldn't rescue me. How many samples are clipped? Well, in a group, there might be 100 in a row, but out of the whole thing, it's 1%, a couple of percent. I mean, it depends how bad you did it, right? Yeah.
He's yelling. Talks about every now and then.
No, amplitude. Well, I mean, the amplitude gets lost, so effectively you're missing samples over some time frame.
So if you get something, and then if you
Okay, I'm going to push on here because there's a couple more things I want to say before I wrap up. Super resolution is the idea of taking something low resolution and making it higher resolution. So here they started with, well, the image on the right-hand side is the original high resolution image. The image on the left is, they dumbed it down by a factor of 2 or 4, probably 4. And then they just zoomed in using a standard technique, which is bicubic convolution. So if you go to any standard image editor and tell it to make your picture bigger, it'll do something like that. They applied a type of a GAN to this and were able to create that picture in the center, which certainly if you look at the details, it's not exactly like the original, but boy, is it ever a lot better than the image on the left. It's really quite amazing. There's a website you can go to, enhance.io, where you can upload your own images, and it'll upscale them by a factor of 4 or more. It does a surprisingly good job, depending on the nature of the image. So what's this got to do with audio? Well, and these are more faces. They look good. They fuzzy to sharp. So this paper that's referenced in the lower right corner here also does super resolution. Again, a UNet sort of structure, and sort of like an autoencoder, if you're familiar with that term. They talk about maybe this is learning a hierarchy of features, and therefore it's able to kind of reproduce things. You get sort of wavelet type things at the bottom, and you get phonemes at the top. I'm not sure I buy that, but that's fine. The upsampling I didn't really understand. But look at these spectrograms now of one of their samples. So here we go at the left. This is the original high-resolution audio signal. After they dumb it down, and they did use a factor of 4 here, they've just killed off all those higher frequencies there. If you do a baseline reconstruction, which is, again, sort of a cubic interpolation, which is up until recently all that was available to us, It does its best to try to recover some of those higher frequencies, but it really doesn't do very, very well. Look at their reconstruction. Look at this. Qualitatively, pretty similar to the original. There's stuff up here, like fine structure that they've been able to recapture. Quite impressive. How does it sound? Well, let's see. I hope we can hear this here. So here's the original high resolution.
The incidents are not believed to be linked.
Here's a low resolution version. This is after they dumb it down.
The incidents are not believed to be linked.
So it sounds like you're talking over a bad telephone line. Here's the best we could do previously.
The incidents are not believed to be linked.
Hardly better at all. Here's their super resolution.
The incidents are not believed to be linked.
It's pretty good. Still, it's a little scratchy and there's artifacts, but you obviously recovered a lot of the high frequency information there. So could be important for speech enhancement, where the high frequencies are really important for intelligibility. Style transfer, we've seen this in images. It's amazing. Audio doesn't work. I won't even play it. It's terrible. So if you want to do that, that would be fun. It's one of those toy problems, though, that it's not entirely clear, although the techniques of style transfer are very similar to the techniques for super resolution, so there's your excuse to play around with that. Reverberation, I think you know how this works. You're in a room. When you talk, there's direct sound into the mic, but then there's reflections from the walls and the doors, and there's reflections from reflections. And in the past, what we've been able to do is, if you've got a good model of the room, if you know exactly the circumstances, you can undo it. And,
自動音声認識にとって残響は大きな障害です。
So that sounded very echoey, like your typical YouTube video. After they apply this room model, wouldn't do that.
自動音声認識にとって残響は大きな障害です。
It sounds really good, but that took a lot of handcrafted models to do it, and that's the state of the art when you know a lot about the recording circumstances. It seems to me you could do this for audio, just make the audio sound better with a lot less reverb. I don't think anybody's working on this specifically, so there's another good thing for you to take on. And I suggest an approach here. People certainly, when they're doing automatic speech recognition using deep learning techniques, they'll do things that are robust in the face of this kind of reverb, but I'd also like to actually have a clean signal come out of it. We talked briefly about objective measures. If you're reading the literature, you'll see a couple of them. PESQ, which comes out of the telecoms world, that's a measure of quality. If it sounds good to a human, just like it's good, clean sound, then it's going to have a high PESQ. There's an alternative measure called STOI, short-term objective intelligibility, which has to do with intelligibility, meaning if you play it to human beings, can they understand the words that are being spoken? You might think these things are the same, they're highly correlated. Surprisingly, to me, they're not so much. And you often have a bit of a trade-off between the two. There's techniques where the authors are all happy about it because they did well with STOI, and they actually did worse than the other guys with PESQ. And this is one of the things that got me interested in this. I wrote a noise reduction program. I was very happy with it. The sound was very clean. It was beautiful. And I realized I couldn't hear the words any better, maybe a little bit worse than before I applied my noise reduction. So then I started looking at intelligibility, and one thing led to another. Here I am today. In my opinion, intelligibility is much more important for various reasons. STOI, the intelligibility measure, looks to me like it's differentiable, which means it could be part of our loss function, and we could train to optimize for a high STOI value. I don't think anybody's doing that. Another project for you. Okay, source separation. We're getting this is going well, time-wise. This is the result that actually got me interested in the whole hearing aid problem. So source separation is this idea that you have a couple of people talking. You're hearing them at the same time. Human beings are pretty good at focusing on one person that they're listening to and kind of tuning out the rest. But if you have hearing loss, that's one of the first capabilities that goes. And so you'll find people, whether they've got hearing aids on or not, who have hearing loss really find it tough in your typical restaurant, coffee shop situation, or in a meeting where there's just a lot of background noise and interfering talking and so on. Super hard problem. It's the cocktail party effect is what humans do well. Computers have never been able to do it very well. This particular technique works on spectrograms, in fact, the magnitude spectrogram. At the top here, we're seeing a spectrogram of the mixture of speech, and at the bottom, we're seeing it colored in a way that shows how it splits up between the different speakers. 3 speakers in this case, and then there's dark blue for just silence when nobody's talking. Now, of course, you've got multiple people talking. They could be talking at exactly the same moment. What these colors represent is who's the loudest at that frequency and at that time. So when I talk about a segmentation problem, this is a segmentation problem, if you think of this as segmenting an image. The way they do this is really beautiful, and I have to admit I'm kind of in love with the elegance of this, maybe more than I don't know, its effectiveness, because unfortunately they had to sort of back off in some of the elegance to make it effective. But the general idea is they train a network to create an embedding, which is to say for every point in that spectrogram, every time frequency point, they map it to a vector in some abstract space, and then they train the network to learn how to do that mapping. Then afterwards, they do that mapping in such a way that it clusters together the vectors that belong to the speakers. So in here we've got red, blue, green. Those are 3 speakers, and you can see there's clusters there. It's a totally made-up example, but that's the general idea. The diagram you're seeing here with the clusters, this is actually a 2-speaker mixture, and these are the actual clusters that they get out of it. So the beautiful thing is you get these embedded vectors, you look for the clusters. That tells you how, well, first of all, you find there's 2 clusters, so you know there's 2 speakers. You look at kind of the centroid of those clusters, you look at the assignment of those dots to the clusters. That tells you, if you think back to your spectrogram, which point belongs to which speaker. So then you create a mask. Do I have a picture of a mask? No. But you create a mask, which you apply to original spectrogram. This is the speaker 1 mask. This is where speaker 1 is dominant, because our clusters told us that. You just set everything else to 0, then you reproduce go back to the time domain using that spectrogram. So let me show you what this sounds like. So here's the mixture.
July delivery platinum surged $13.10 before settling at $622.90 an ounce, up $12, period.
So that was 2 clean recordings of people just smashed together. And even you listening carefully to that, it's hard to tease out what they're saying. All right, here's after the separation, speaker 1.
The mid-July increase came even though automakers are offering incentives on fewer cars this year than they did last year or earlier this year.
I don't know how well you could hear about that, but that was way, way more intelligible. It was a very good suppression of the other speaker. Let's hear speaker 2.
July delivery platinum surged $13.10 before settling at $622.90 an ounce, up $12, period.
It's not super high quality speech, but very intelligible. That's a super impressive result. And if you listen to other source separation techniques that preceded this, this is a dramatic improvement. I think it's one of the most impressive.
Was that a blind? Was that blind?
That was blind. Yeah. So they trained it on a set of speakers. The test examples we're hearing here are from not in the training set.
But you trained them, did you train them?
Well, they use the individual speakers as ground truth for the training, for sure. Yes. I'm gonna do one more of those because I like those. Let's see this one.
He said such products would be marketed by other companies with experience in that business.
Mr. Plaskett told union leaders he believes he could have a firm proposal in hand.
He said such products would be marketed by other companies with experience in that business.
So you might not be thrilled with the quality of the sound that comes out, but if you fed that now into like a speech recognition system, it probably wouldn't have much trouble with it. It doesn't care about a little bit of scratchiness. So that was impressive. That was all done with a spectrograms, magnitude, the phases all just mashed up in the way I described before. People are doing this in the time domain as well. I don't, sadly, they didn't post any examples, so I can't play any of that for you. Music-voice separation, this to me falls in the category of toy problems, but there's some really interesting work which I don't have time to talk about. But some people at Spotify who have access to like huge amounts of music in their database, including, apparently, when artists release a song, they'll also release just the instrumental track. So they just comb through the database to get millions of examples of speech plus, or vocal plus music and music alone. They trained this thing to separate them out. The results are pretty good. They used a magnitude spectrogram for their work in this UNet structure. I wrote to the authors and said, how about a compact spectrogram? And they said, yes, that's the next thing we're doing. So that'll be interesting. I'm not going to do that. I'll briefly mention beamforming. This is the idea where you have multiple microphones. One thing that's very interesting about sound that you don't have with imagery is that sound comes at us from all directions. You don't have to be pointed particularly to hear it. But if you are pointing somewhere and you've got two ears or you've got multiple microphones, you can get differential gain depending on whether you're pointing at the sound source or not. There are beamforming is a well-established technique. There's lots of sort of fixed algorithms to calculate the beamforming. I always assumed it was going to be a pre-processing step. So if you've got a hearing aid, most hearing aids, by the way, have a couple of microphones in each ear, not just one. So you've got a microphone array to work with there. I assumed that you would do, again, this kind of fixed pre-processing stage with beamforming before you feed it into something else. This paper that's mentioned at the bottom here, they learn the beamforming in a network. So now they're much more an end-to-end process because even that front-end stuff is part of it. Okay, the last one I want to talk about, and then I want to say something about hearing aids specifically in the last couple of minutes, is VQ-VAE. So these are the WaveNet folks again. Love that WaveNet guy. It's kind of a complicated paper. This one just came out. But basically what he's doing for both imagery and speech is doing this kind of bottleneck type of architecture again. And if you think about what you get at the bottom of that U in the UNet, where you've got that kind of choke point there, he's describing the information that you've got there as latent variables. Let's just call them latent variables. So he takes, this picture is showing an image, but we're going to do it for sound. You take your input, you encode it into these latent variables, and then you decode it into something else. So what's the relevance for us is, well, I'll play you this, and then I'll tell you what's going on.
We are encouraged by the news.
We are encouraged by the news.
And I won't play all the other examples, but so what happened there? So he had a recording of a person, he encoded it, then he decoded it, but he decoded it with somebody else's voice. So he's transferred the speech from one person to another, and it kept much of the same cadence and that kind of stuff. You'll see in a minute why I think that's so important. Okay, toward a better hearing aid. So what have we seen so far today, or heard? Lots of good progress on many fundamental tasks that we care about for audio. Lots more work to do, but the early results are definitely encouraging. I would say it's fair to say the quality is not spectacular yet, except this text-to-speech stuff. That's pretty darn good. But the accuracy, the intelligibility is often better, and like a automatic speech recognition system would probably benefit a lot from these techniques. So my thoughts on a hearing aid is, if we're so good at ASR and we're so good at text-to-speech, why don't we admit that and combine them together? So here's a couple of options for a processing chain having to do with a hearing aid. And there's two options here, the yellow path along the top and this green path at the bottom. So you start with your input sounds. It's just picked up by the microphones, the ambient sound. You do some sort of beamforming. You'll do that source separation we talked about because you really want to focus in on a particular person you're listening to. You'll end up with then the isolated source. There's a little bit of a question of how you pick out the source you're interested in, but let's just assume that we know which one we care about. And then what do you do with that? You've got this isolated source, which is kind of this scratchy, not spectacularly high quality sound, perhaps. Well, you could enhance it. You could do this path, and you just try to make it sound better and better. You create the output sound, and you hope that the person wearing the hearing aid, that you've done a good enough job that they can now understand what was being said, whereas before they couldn't. And that's kind of what hearing aids do now. One way or another, they enhance the sound. I don't think that's ever going to be spectacularly successful, just as current hearing aids are not spectacularly successful today. The alternative would be to do a little bit more what we just saw with this VQVA thing, which you take that isolated source and then you encode it. It's probably going to be a little bit insensitive to the noise and the artifacts that came through the source separation and so on. You encode it to this latent space, and then you resynthesize the voice. And that's what you feed to the hearing aid. So the idea is the hearing aid is something that completely blocks out the ambient sound. All you hear is the soundscape that we create for you. But there's microphones there that are listening. They get this sound. They separate out the thing that's of interest, encode it, and then resynthesize it. So what you're hearing is now a synthesized voice. Hearing loss is often a case where you need some frequency compensation because you have differential response at different frequencies. So fine, you can do that. You can make that synthesized voice anything you want. It can be very tuned to the particular nature of the hearing loss that the person has. So lots of people told me I'm crazy to think about this yellow path as the way to go, but I think it's high risk, but the more promising one in the end to work. So that's my case for that. A bit of evidence that it might work, who knows? We're getting to the stage where you can have automatic translation in your ears. So Google has announced the Google Pixel Buds. You put them on and it'll translate, not exactly simultaneously, but close to real time from one language to another. So there, the latent representation is the words of the language. Here's one language, represents it as something else, and then synthesizes a voice in a different language. There's another product called the MyMenu Click, which I got my order in for that, and the Google Buds as well. So I haven't tried either of these. Okay, wrapping up. I have lots of recommendations for deep learning audio researchers. There's a lot to learn from the ImageNet experience, not from the algorithms, but the experience of doing that and the success of that competition. Please, please, please get your training data out from behind paywalls. I keep trying to reproduce results in papers, and they keep benchmarking against stuff that I don't have access to. It's just dumb. Open it up, please. This stuff's available. Get your papers out from behind the paywalls, too. Archive.org is where everything is. It's getting better, but I'm looking at you, IEEE. Publish more examples of your output. Don't put out a paper about how you've done a great job cleaning up audio and then don't give any examples. That's not convincing. It's a little bit brave to put out these examples when the results are preliminary and early, and many people will listen and say, well, that sounds like not very high quality. In fact, you got to do it. Publish more code. Publish your train models. Don't just put code out there and say, it took us 2 weeks to train this, and here's the thing, and now you can train it. Like, I don't have 2 weeks to try to retrain it. And contribute to deep learning frameworks. If you want to do this transfer learning by using a pre-trained ImageNet network, you can do that in 2 lines of code in Keras. If you want to do any of this audio stuff, you've got a much more of an uphill battle. Now, I claimed I was going to try to recruit you into working on deep learning for audio. You should. Why should you care about this? Well, there's a rich source of really interesting problems here. I think you've seen some of those today, and there's many, many more. There's lots of low-hanging fruit. Literally, as I was preparing this, and I realized, oh, there's sort of a gap here. I wonder if anyone's thinking about that. Sometimes they are. Sometimes a paper would appear that day that somebody's thinking about it. There's lots. There's training data is readily available. You can't say that about lots of other data science problems. The early results, I think, are promising. I hope you've heard things today that you thought were interesting. The field is just generally less crowded. Let's face it, if you're doing some image thing, you've got lots of people doing that, and they're getting a lot of marketing oomph from what they're doing. But finally, the problems are really important. I think making a better hearing aid, and you want to hear me talk about that for an hour, making a better hearing aid is a super important thing that we could all be contributing to as a deep learning community. That's it. Thank you.